Okay, so welcome Algebra 1B students to your first screen recording. So the purpose of this video is for us to go over the answers to your introduction to exponential growth functions. So this was the introduction of the investigation that you guys started last class, and you would have had a few minutes to wrap that up in class today. And so what I'm going to do is just take you through the answers. And so first we'll go through the answers to the questions on the first page. And so the question is, what is a function? And hopefully what you got as your answer to what is a function is simply an equation or a mathematical rule. And so you've dealt with lots of different kinds of equations. Anytime you get an equation like y equals 2x plus 4, for instance, that's an example of a function, which is, as I said before, simply an equation. Okay, and the second question asked you, what are functions used for? Now, this is more important, and this is going to start to get to the heart of what we're trying to do in this unit and with exponential functions specifically. And the answer is that the most useful use for functions is to model and to predict. So what I'm talking about is mathematical models. Again, like the one I referred to above, this is a linear model or a linear equation, and it allows us to make predictions and models. And again, the idea of a model is that it is something that reflects what happens in reality, in real life. Okay, so moving on to the third question you were asked. The third question was, what notation do we use for functions? So whether you realized it or not, actually you've been using that notation all along in the investigation itself, and actually you've been using it as well in the linear function section. And the answer is we use function notation, and what that really means is using things like f of x, g of x, h of x, and those really basically are used instead of the letter y. But the fact that it's a function has certain implications, and we're going to discuss those implications a little bit, but they're not really important for this specific investigation. Okay, and then moving down to our last question, and that is a tricky question, something that typically causes students a lot of difficulty, and that is, what is domain and range? And so the answer, the brief answer, and of course we'll get into some applications later, the brief answer is that domain is the set of all x values, and the range is the set of all y values. Another way to look at it, because of course you don't only have to use x and y as your letters, the domain is the set of values of the independent variable, whereas the range is the set of values of what is known as the dependent variable. A dependent variable is a variable whose value depends on the other. So as we saw for our function above, if we have y equals 2x, if we have y is equal to something like y is equal to 2x plus 3, if I want to know the value of y, I need to know the value of x. So the value of y depends on whatever value of x we put in there. And so for instance, maybe I put 2, and if x is equal to 2, then y would equal 2 2s are 4 plus 3 is 7. That's 1 point on this function. Okay, so let's move now to the second page. That's all the questions for the first page. We'll jump ahead to the second page. So what you needed to do, and most of you got this done in the previous class, was to complete each of these tables of values. Now this is an important method. A table of values consists of, as you could see from these, x values, and the x values are the independent values. So those were values that we picked, and whatever those values were determined what the corresponding y values were. In this case, though, we're using function notation, and so instead of saying y equals, we're saying k of x equals, and that notation implies that the value of the function is dependent on x, and in this case the k of x function was in fact a linear function, which you may recall linear function is just a line. Okay, and each of these y values or k of x values was obtained using the process of substitution. We subbed in minus 2, times it by 3, added 2, and we got minus 4. Okay, the procedure, so I mentioned before that a table of values is a very important method. The reason it's very important is that you should be able to see that we have used the exact same approach for graphing an exponential function as we did for a linear function, and that is to use a table of values. We once again have a selection of x values, the independent variable, and we sub them into the f of x equation, or the y value, and produce a set of ordered pairs or coordinates which we can then graph and join, and that will give us a representation of the function. Okay, so that was the next part, assuming that you got your values correct. And let me just go over that very briefly. In order to get the 1/9, we sub in minus 2 into the equation, so it becomes f of minus 2, which means I'm subbing in minus 2 is equal to 3. In the place of x, I sub in minus 2. If you recall your exponent rules, you should recall that that means we move it to the bottom and change the power to a positive. And then, of course, if I evaluate 3 squared, that's where the 9 comes from. All of the others just follow the same approach, so I won't go over all of those again. Okay, so what I'm going to do now is actually go straight down to all of the graphs, and the graph I'm going to reveal now will show all 4 of the functions graphed. Your linear function, which was the k of x function, the first exponential function, which was the f of x function. And so what I'll do is let me move my cover down. So a couple of key things that we want to note. First of all, here in purple is our k of x function, our linear function, which is, as you can see very clearly, a straight line, or just a line. There's only straight lines. And you can contrast that or compare it to the f of x function, and here you see the f of x function is in red, both the graph and the label, and you'll notice that the f of x function has got a curved shape as opposed to being straight like the line. Okay, and that's very clear as well. If you compare the table of values, you see how quickly the exponential function starts to grow. Once x gets larger, the exponential function starts to grow very quickly, whereas the rate of growth for the line is constant. And so if we look carefully, from minus 4 to minus 1, that we have added 3, and 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 that pattern continues forever. And you can see therefore that the growth rate is constant, whereas when we go from 1/9 to 1/3, hopefully what you realize is we have multiplied by 3 in each case, and so multiplying by 3 in each case will cause the graph to grow much faster. As we know, when we multiply by a number larger than 1, it grows, and it'll grow much faster than the line. And so that explains, hopefully that should explain for you, why the exponential curve, as the x values start to get bigger, starts to turn up sharply, and of course that continues forever upwards. Okay, so I'll talk about the g of x and the h of x functions. And so hopefully what you noticed with the g of x and the h of x functions, let me try and select a color we haven't used, I'll use black over here, is that in all of the functions, f of x was 3 to the power of x, g of x was 2 multiplied by 3 to the power of x, and h of x was 3 to the power of x plus 2. They all had that 3 to the power of x term, and all we did was from the f of x to the g of x, we doubled all the values, and for h of x, you just added 2. And so let me close my revealer here and jump down to the table of values, and hopefully what you should have been able to see is that for the g of x table of values, so each of these values in here were simply twice as big as the f of x. And so if I reduce the size here, Let me just reduce that, and hopefully what you'll be able to see is I can show you both tables of values if I can just about squeeze them in. Let's just make that 35. Okay, and that should be okay. And so what you can see is that up here we have got the f of x values 1/9, 1/3, 1, 3, 9, and the g of x 2/9, 2/3, 2, 6, 18, twice as big as each of these values. Similarly, for the h of x function over here, each of these values is simply 2 more than each of the f of x values. And the last thing really for us to take into account will be, if we look carefully at the graphs, that if we compare the red graph, the f of x, to the green graph, which is the h of x, to the blue graph, that there are some slight differences. If we take any point on the h of x graph, the f of x graph should be 2 units below it, or the h of x graph should be 2 units above it. They have the identical shape, but the h of x graph is just 2 units above. And then if we were to compare instead the g of x to the f of x for any given value I choose, so if I were to pick this value over here for the f of x, then the g of x is twice as high. Its y value is twice as large. And so in this case, the x value is 0, we have a y value of 1, and for the g of x we had a y value of 2. So as you can see, twice as high. Similarly, if I come over here, well, we'll leave it there for now, because otherwise I'm going to have to pick a specific point, and we don't want to concern ourselves with that. But the key here is that the blue, green, and red graphs have each got basically the same shapes, but some are steeper than others, and some of them, as you can see from the green one, tail off here, and they tail off above where the other two graphs tailed off, and we're going to talk about that in just a moment. So if I now look down to the bottom, so what are the differences? The growth rate is constant for the line. For exponential functions, the growth rate, the rate of change, increases. So I mentioned that earlier. And the last thing is this question over here, which was a difficult question to answer because you may not have understood the notation. And so what this says is, determine what happens when x approaches minus infinity. In other words, when x goes from -1 to -2 to -3 to -10 to -50 to -1000, and it's going down a number line. So if we had a number line over here and we had 0, in other words, what's happening is as I move further and further and further down the number line on the negative side, the question is, what is happening to y? And similarly, as x approaches infinity, as I move all the way along the number line in the positive direction, what is happening to y? And as you can see, as x approaches minus infinity, y approaches 0. If I go up to the graph, you can see that for the f of x function, as x gets smaller and smaller and smaller, the function gets closer and closer and closer to the x-axis, which is where y is 0. And likewise, as x gets bigger, y gets bigger. And if you go back to your graph and we'll look again at f of x, as the value of x increases, the value of y also increases, and that's why we call these growth functions. The value of x increases as the value of y increases. There does appear to be one exception, hopefully you picked that up, and the exception is the h of x function. As x approaches minus infinity, h of x does not approach 0. In fact, it approaches 2, and that is something we'll talk about when we continue the lesson later today.